13D. For each of the following boxes, say whether color and number are dependent or independent. Box A. So in order for this to be independent, we have to check conditional probabilities. What is the chance of drawing a 1? 2 out of 6 or 1/3. So the probability of 1 is 1/3. What is the probability of 2? 4 out of 6, which is 2/3. To check for independence, we have to say, what is the probability of 1 given white? So some of you aren't paying attention. Watch this. Look up here, guys. So what is the probability of getting a 1 if you know that you have a white? 1 out of 3. What is the probability of 1 given you have a black? 1 out of 3. Is that the same? So the probability of 1 is the same as the probability of 1 if you already know the color. Okay, let's try 2s. What's the probability of 2 given white? It's still 2 out of 3 because 2/3 of the white are 2s. What if I change to black? Same. So color and number are independent. And this sort of thing happens on face cards. What's the chances of drawing a 2? 4 out of 52, which simplifies to 1 out of 13. What's the chance of drawing a 2 if you know it's a heart? It's still 1 out of 13. That is independent. Okay. Now, let's say you lose one of your spade cards. Okay. Let's say the 5 of spades is gone. What is the chance of drawing a spade? 12 out of 51. Okay. What's the chance of drawing a 4 if you know that the card is a spade? It would be 1 out of 12. Are those fractions the same? No, so they are dependent on each other. Okay, letter B. A is independent. So B, is the chance of drawing a 1 the same as drawing a 1 if you know the color? Yes. Okay, and is it true for all the other numbers and colors? Yes. So B is independent. Now C, what's the chance of drawing a 1? 2 out of 6, which is 1/3. What's the chance of drawing a 1 if you have a white? 1 out of 3. Okay, let's try with 2s. What's the chance of drawing a 2? 1/2. 3 out of 6. Okay, what's the chance of drawing a white if you know the card, or sorry, drawing a 2 if you know the card is white? 1 out of 3. So those are dependent because the ratio of 2s is different than the ratios of 2s given white. And the same is true of 3s. Yeah, they're not equal. So in 3s, what's the chance of drawing a 3? 1 out of 6. What's the chance of drawing a 3 if you have a black? 0. So those are dependent. The ratio of numbers and colors gets messed up because they're not equal. Okay? 2A. In the box shown below, each ticket has 2 numbers. So we have a 1-2, a 1-3, a 4-2, and a 4-3. For instance, okay, a ticket is drawn at random. Are the 2 numbers dependent or independent? So we're pulling one card out. Are the 2 numbers on the card dependent or independent? So if you get a 1 on the first card, what's the first number? What's the chance that the second number is a 2? 1/2. What's the chance that the second number is a 2 despite which card you pull out? 1/2. Okay. What's the chance that the second number is a 3? 1/2. What if the first number is a 4? What's the chance that the second number is a 3? 1/2. Independent. Right? There are just as many 3's that start with a 1 as there are 3's total. Well, there's the same percentage. Okay. Repeat for the other box. 1, 2, 1, 3, 1, 3, 4, 2, 4, 3, 4, 3. So what's the chance of getting a 1 to start? 1/2. What's the chances of getting a 1 if you know that the second number is a 3? It's 2 out of 4. It's still 1/2. Okay. So what's the chances of ending with a 2? 1/2. What's the chances of ending with a 2? Or no, sorry, it's 1/3, right? The chances of getting a 2 in the second number is 1/3. What's the chances of getting a second number being a 2 if you know the first number is a 4? It's still 1/3. There are 3 4's, and one of them ends in a 2, so that would be independent. No matter how you build that, the percentages are the same. Okay, the box C, what's the chances of ending with a 3? Half of those tickets end in a 3. If you know that the first number is a 1, what's the chances of ending with a 3? 2 out of 3. So we found one case where there is a dependence. So the box is dependent. Does that make sense? Are you getting the hang of that? No? Okay. So let me write them out again. So let's do B. 1, 2, so 12, 13, 13, 42, 43, and 43. Okay. And this is something that's important to know, so we can spend a little bit more time on it. What is the probability that the second number is a 3? Well, 1, 2, 3, 4 out of 6, which is 2/3. Right? Now, what is the probability that the second is 3 if the first is 1? So we throw out all of those. And we get 2 out of 3. So what we say is the 3 is independent of the first number. The chances of getting a 3 in the whole box is exactly the same as getting a 3 if we know the first number. Okay, and that's true whether we do 1 or 4, right? If we know the first number is a 4, the chance of getting 3 is 2 out of 3. If it's a 4, the answer is still 2 out of 3. And if we check every single one of those, we're going to get the same ratios. For instance, what's the chances of getting a 1 if the second number is a 2? 1 out of 2. We either choose from 12 or 42. What's the chances of getting a 1 overall? 3 out of 6, which is 1/2. And no matter which ones we pick, we will always get the same ratios, just like face cards. The chances of getting a 6 is the same as the chance of getting a 6 if you know it's a heart. You have a 1 in 13 chance either way. But the next box is messed up. So we end up with 12, 13, 13, 42, 42, and 43. So what is the probability that the first number is a 1? 1/2. 3 out of 6, which simplifies to be 1/2. What is the probability that the first is 1 if the second is a 3? So now we have 2 out of... Oh, sorry. What is the chance that if the second is a 3? So I get 2 out of 3. And right, so what is the chance that the first one is a 1 if we know we can only pick from those things that end in 3? So I get rid of this and that and that because they don't end in 3. Yeah, we're only allowed to choose from the ones that end in 3, and 2 of the 3 start with a 1, and that 1/2 and that 2/3 don't match. So these are dependent. Color, or not color, but the positions are dependent. If you know that you have a 1, you have a different in the first space, you have a different probability than if you don't know. Okay? So independence is just like face cards. The chances of getting what's the probability of drawing a heart? 1 in 4, right? Every fourth card is a heart. If you know you're looking at an 8, what is the probability that that card is a heart? 1 in 4, because there are 4 8s and one of them is a heart. So suit and number are independent in a deck of cards. If you throw a card out, now suit and number become dependent because you no longer have the match, right? You no longer have 4 of every. Right, right. All right. Next question. Put it in. All right. Number 3. Every week you buy a ticket in a lottery that offers 1 chance in a million of winning. What is the chance that you never win, even if you keep this up for 10 years? Well, how many weeks are in a year? So 13 times 52. So you're only going to play 676 times, right? So you have a 1 in a million chance of winning. Oh, sorry. I pushed the wrong button. 10 times 52. So you play 520 times. So your chance of winning for each one of those is 1 out of a million. So you play twice. Now your chance is 2 out of a million. And you play 3 times, your chance of winning is 3 out of a million. So your chances of winning are 520 out of 1 million. But what's your chance of losing? It would be 1 million minus 52. So 99948 over 1 million. And actually that's not totally correct because 365 divided by 7 is actually 52.1 or 520.4. Well, but leap year, well, yeah, extra day. So really you have a 521.4 chance of winning, right? Because a year is not exactly 52 weeks. It's just slightly longer. 2 days, 1 day. Yeah, just a little bit longer. Is that what the book had? Your chance of losing? It had 99999 over a million? What page? Oh, boy. We did this wrong. I'm sorry, guys. We have to multiply them, right? So it's 1 over a million times 1 over a million times 1 over a million times 1 over a million. So it's going to be, yeah. Okay. Sometimes I mess these up. 4. Two draws are made at random without replacement from the box. 1, 2, 3, and 4. The first ticket is lost and nobody knows what was written on it. True or false? The two draws are independent. What's the chances that the second one is a 5? Or, sorry, a 4? 1 in 4. But wait a minute, there was a first card. We don't know what it is. So the second card could be any of the 4. So are they dependent or independent? They're independent because we didn't know what the first card was. Technically, it should be dependent, but you don't know that until you reveal that first card. True. The two draws are independent. True. Oh, does it say false? All right, let's see their explanation. What page is it on? It's like, okay, so, but that goes against what they did before.
It says you don't know, so you just still 1 out of 4, but
Oh, so I guess what they're saying is the 1 in 4, okay, that makes sense. So what is the probability that the second card is a 2? 1 out of 4. But that second card did depend on the first card, even though we didn't know what it was.
yeah.
Right, because the second card can't be whatever the first card was, even though nobody knows what it is. Okay, that makes sense. Won't be the last time I get things wrong. One student is chosen at, oh, no. Suppose that in a certain class there are 85% men, 20% women, 15% freshmen, and 85% sophomore. The percentage of sophomore women in the class can be as small as... So we have 80% men and 20% women, and we have 15% ninth graders and 85% 10th graders. And the question is asking, the percentage of sophomore women in the class can be as small as... So we want to find 10th grade women. Could all of the 10th graders be women? No, why not? There aren't that many women out there. Okay? Can all of the 10th graders be men? No. What's the highest number of 10th grade men? 80%. So if all of these guys are 10th graders, then how many have to be women? 5%. So the smallest number of 10th grade women would be 5%. If they were all men except for, right, if all the men were 10th graders, then 5% would be women. Okay? The percentage can be as large as 20. All right? One student is chosen at random from the class described in the previous exercise. The chances of getting a sophomore woman can be as small as... Do you see that? It's the same problem. Well, the first one is how many women fit this category? Anywhere from 5% to 20%. And the probability will be the same of drawing one at random. Could be as small as 5% and as large as 20%. In 2002, about 50.9% of the population of the United States was female. Also, 1.6% of the population was 85 and over. True or false, and explain. The percentage of population consisting of women age 85 and over is 50.9 times 1.6% is 0.8 of 1%. True or false? False. How come? Well, women live longer than men. So the overall population is 50.9% women. But of the older people, we would expect a higher percentage of them to be women. These are dependent. Is your age, is how long you live dependent on your gender? Yes, because women live longer. So we cannot do that multiplication because they are not independent. They're dependent. Is that what the book said? Yes. Oh, hard. Okay, let's try this. In a certain psychology experiment, each subject is presented with 3 ordinary playing cards face down. The subject takes one of these cards. The subject also takes one card at random from a separate full deck of playing cards. If the two cards are from the same suit, the subject wins a prize. What is the chance of winning? Let me try that again. So you get 3 face cards face down. Let me draw this out. So we get 3 cards, and we don't get to see them. The subject takes one of these cards. So we pick one of these, and then we pick one of the cards from a separate full deck. If the 2 cards are from the same suit, the subject wins a prize. What is the chance of winning? So from the separate deck, we are going to pull 1 card out. So this has a 1 in 4 chance of every suit, right? Okay. And then here, let me see. Ooh, there was a... Huh. So the 2 decks are definitely independent, but these cards are dependent. Does it matter which card you pick? So does it say 1 in 16? One in 4? Well, but each card has a 1 in 4, right? Okay. Each subject is presented with 3 ordinary playing cards face down. Oh, that makes sense. So, whatever card you get on the first one, right? No matter what suit it is, when you draw the second card, you're hoping for the suit of the first card. So the suit on the first card, it does whatever you get. If you get a heart, the chances of pulling a heart from another deck is 1 in 4. Wow, that threw me for a loop. Yeah, it's hard. All right.